All right, we are now starting chapter 6, which is on work and energy. It starts on page 292 in your textbook. And we'll get going. Okay, and so we talked a lot about energy. Well, not a lot, but we talked about energy last year. We talked about kinetic energy, potential energy, mechanical energy, and what that all means. So we're going to do a quick review of kind of some of those and then continue on looking at how energy affects work and so on. Okay, so again, kind of a reminder. So maximum gravitational potential energy is stored in the skier at the top of the run. Okay, that energy is then converted into kinetic energy and heat as the skier starts going down the run. Okay, and so again, you can always find your total energy is the potential plus kinetic. If they're at the top of the hill, there is no kinetic, so all of your maximum energy would be your maximum potential energy. And then the definition, energy is the ability to do work. Okay, so work is done when a force acts over a displacement. Okay, work is a measure of the amount of energy transferred when a force acts over a displacement. So definition of work. Okay, the formula for work is equal to force times the cosine of your angle times your change in distance. Okay, and the reason, if it's just, if you aren't pushing something at an angle, you don't have to worry about the cosine of your angle. If you're pushing it, if it was just pushing straight instead of kind of pushing it down, then it would just be force times distance for work. Okay, and only the component of force that acts parallel to the displacement is what is doing work. So in this case, this person is kind of pushing, but because they're taller than the box, they're pushing down and forward at the same time. So this is their overall force. Okay, we only are worried about the force that, if this is the direction of displacement, this is the force direction that we're worried about. So really, we just want to find our force in that direction. So our force parallel to our displacement is equal to, if this is our angle here, force, our overall force times the cosine of our angle. Okay, so the maximum amount of work is done when the applied force is parallel to the displacement. So when this rocket is shot, all of the force is going upwards and our change in displacement is going upwards as well. So then we don't have to worry about that cos of our angle. Okay, other times too, we have to, again, if someone lifts a box from the ground, the distance they lift it up is against the force of gravity, and so there would be, so that would be parallel to the force. Okay, there is no work done when the force is perpendicular to the displacement. So once this person lifts the box up and moves, they're on skis here, but if they're walking or anything like that, there is no work done once he already has the box up. The only work is done is the force over a distance. There's no force change here, so there's no work being done. Even though, if you were holding this box up, you'd feel it in your muscles, but technically no work is being done because the force is perpendicular to the displacement. Okay, so example, again, all the examples out of your textbook. Okay, go through and read over them. If you're having any troubles, I'm going to do a whole separate video with just a bunch of different examples. So look for that to come out, and you can watch through it and again skip forward and back and whatever you need to do to kind of help you out. Okay, so now we're moving on to gravitational potential energy. We talked about this last year. Okay, it's the energy of an object due to its position above the surface of the Earth. Oops. Okay, and so our formula, potential change in potential energy is equal to work, or force over distance. Okay, again, force is equal to mass times acceleration. So if we're lifting something up, okay, it's going to be like the force of A is going to equal, like if we lift something up, it has to be equal and opposite of our Fg. Okay, so really our potential energy formula, okay, is going to be our m times g, so our mass times acceleration, which is equal to force, times our change in height. Okay, and when an object is moved upwards, we aren't changing its displacement. Well, we are changing its displacement, but its displacement will be the change in height. Okay, so any of these gravitational potential energy problems that you'll be doing, it doesn't matter. Like sometimes they'll say the person walked up a stairs this distance. All you need is the height of the stairs. So like from the bottom to the top, okay, in a straight line, that's going to be your change in potential energy. It doesn't matter that the stairs were at a 60-degree angle and anything like that, unless you have to find the height using that angle. But like sometimes they'll say like they walked up a stairs that were 10 meters long and your displacement's 5 meters, okay, for your change in height, that's all that matters. You can forget about the other one. Okay, so to lift an object at constant speed, the force acting on it are balanced out, so that's why we get our overall formula. Change in energy is equal to mgh. Okay, and so, again, example, this is on page 296. Basically, so these people at the bottom, okay, they would have no potential energy, okay, compared to when they're at the top. Once they get moved up, okay, now like depending on their mass, okay, they're going to have a lot higher potential energy. So an object on the ground, yeah, is usually considered to have zero potential energy. Okay, to calculate the potential energy of an object with respect to the ground, we can always just use our potential energy equals mass times gravity times height. And for gravity, you can leave it positive because energy is not a vector quantity, so we don't have to worry about like having it negative or positive. Okay, so yeah, there's an example, yeah, page 296. Okay, when we're doing these problems, sometimes we'll have different reference points. Basically, it's the point chosen, or like it's an arbitrary point chosen from which the distances are measured. Okay, and so if you have this book up here on this shelf, okay, it has the potential energy from the floor. So for the height of the floor, if the table was right under it, it could also fall down to the table. So if the reference point was the table, then like you just want this height from the table up to the shelf. Okay? Or like if you lifted it up to the ceiling, between the ceiling and the shelf, it could be a reference point also. So you always want to know what is the reference point. What am I measuring to kind of find your overall change in height. Again, change in gravitational potential energy only depends on the change in vertical height. So I talked about that a little bit earlier, but like if it says like this cart's moving up this slope, whoops, this height is all I need. At this point, what is the height? It doesn't matter what this distance is. It doesn't matter what this angle is, well, unless these distance and angle give me the height. But in most cases, I'm just looking for this number here. Okay, another example, kind of this one, you're looking for the potential energy at the top of the table, and then like with reference like to the table or reference to the floor, and so on. So you can look over that. That's on page 298. Okay, moving on. Now we're going to look a little bit at springs. Okay, and so when we're talking about springs, it has to do with Hooke's law. So Robert Hooke was a English physicist, and basically he showed that the stretch produced by the force applied to a string was proportional to the magnitude of that force. So basically, if we put a weight on this, so as is done here, our change in distance is due to the weight, okay, which is equal to the Fg. So like every time, like if you double the weight, you'll double the force of gravity and you'll basically double the distance. Okay, so the stretch produced by a force applied on a spring is proportional to the magnitude of the force. The more force, the more stretch on the spring. Okay, and so if we look at it like on a graph, okay, so again, like for the mass, this would be the mass put on the spring. Okay, the weight would be our mass times 9.81. Okay, again, mass should be in kilograms, so that's why like these numbers are smaller in newtons than these masses, because this would be 0.2 times 9.81 would give us the 1.96. Okay, and then our position, 0.05. Okay, if we double the mass, okay, pretty close to, or we are doubling the weight, okay, and the distance, it's not exact, but basically you're doubling the distance. Like the double would be 0.1 instead of 0.99. Okay, and then same thing here, like it's going up fairly even. So like when we plot it on our graph, we get a straight line and we can basically say it's doubling. So when put this on a graph, okay, we can see that, yeah, the slope equals rise over run, which is the rise is the change in force, and the run would be the position, like how far it is away from that starting point. So from that, you can find the spring constant, which is the value of K. I know it's the same as Kepler's constant, you just have to remember that they're different. Okay, so K is equal to force over our change in position. Okay, so it indicates basically the stiffness of the spring. Okay, the higher the K value, the stiffer the spring. So like your vehicle has spring, or some vehicles have like springs or shocks in them. I guess all vehicles would have one or the other. Okay, those springs are going to have a really high K value. Okay, a small spring that's in your pen so that it clicks and things like that, those would be really small K values. Okay, Hooke's law. Okay, the formula that we're given on our formula sheet is the force equals, actually on our formula sheet it says negative K, but we'll just keep it as force equals K times X. So our spring constant times the position. Okay, elastic potential energy, so the amount of energy stored in a spring is equal to the work done on it. Okay, and so again, if we have our position and force graph, okay, the change in energy is equal to our work. Okay, and so basically the area under the curve is equal to our energy. So work equals 1/2, because again, for area of a triangle is 1/2 base times height. So in this case, work would be 1/2 force times our position. Okay, again, force is equal to kx. So if we substitute kx in for force, okay, we got, so okay, 1/2 kx times x, which is equal to, work is equal to energy, which is equal to 1/2 kx squared. And so to find it, due to the finding the area under this graph. Okay, and so this example is on page 301. Okay, using Hooke's law and graphing to kind of solve for the potential energy. Okay, so potential energy, again, potential energy is the energy stored that, like, it has the potential to do something. So if you lift something up, it has the potential to fall. So that would be this guy here. He has this rock. Hopefully this girl's not standing underneath him. Okay, but he's holding the rock up here. It has the potential to fall. So now kinetic energy is energy due to the motion of an object. So when this guy is holding this rock up here, it has no kinetic energy. When he lets go of the rock and it starts moving, our velocity, we start gaining velocity, and you need to have velocity to have kinetic energy. So our formula for kinetic energy is equal, EK is equal to 1/2 mv squared. Make sure your mass for all of these are in kilograms. Okay, and then your V is going to be in meters per second. Okay, and so make sure you convert if it's in kilometers per hour. Okay, and so yeah, whoops. That's what I just talked about, but yeah, kinetic energy is in joules, mass kilograms, speed meters per second. Okay, another couple examples. Okay, on page 303 and 304, kind of just talking about kinetic energy and solving for it. For this one, like for this example, it talks a bit about kinetic energy and the energy of the springs due to like the stretch in our trampoline here. So look over those examples. Okay, all of everything I just talked about is on pages 292 to 304. Like I said, I'll do a couple of examples to kind of show you how you do them, but a lot of this stuff we talked about, other than the Springs and Hooke's law, everything else we've done before. Okay, the formulas are all on your data sheet. They are under work and energy, and then the ones for the springs are under the harmonic motion, waves, and light. Okay, and just remember, yeah, K, now we're referring to the spring constant and not Kepler's constant. Okay, and so those are two different K values.